Well, that would be mean after the lecture on Wednesdays. So what I try to do now is to find a room for that. And then I do not expect that that will happen by tomorrow. So it will take probably a little more than that. But next Tuesday, I'll know. So then I'll tell you, and I'll publish it earlier if I get it earlier on It's Learning. What we will have is, anyway, the first lesson on Monday, on next coming Monday, from 18 to 20. The idea is then to give you in that lesson, when we start now answering your questions on the new exercise, and for further lessons, when we have gone through the exercises, to give you feedback on the old exercises. So that's the plan for the Monday lesson. And the Wednesday lesson is then devoted to guidance. Jürgen and me will be there, and we answer your questions on programming, MATLAB, Fortran, CLP tool, whatever, and the numerical methods. Now I would like to know for whom this time that the majority voted for is not possible. Let's see. 1, 2, 3, 4, 5, 6, 7, 8. So 8 people it is not possible. So that, but for all of you, I think Thursday, 18 to 20 is possible. Is that right? Because that was selected by the administration to be such. So then, for the time being, we'll then have it also there, but then I will only be there, Jürgen not. So then we will, but so for the time being, then we'll have lessons also then on Thursdays, 18 to 20, to for those people for whom the new time is not possible, but also people who want to have extra guidance can also come. So then, but I'll write that also on It's Learning. Any question on that or regarding the lessons? So we'll start with a lesson on Monday. There will not be a lesson now on Thursday. We'll start on Monday, 18:20, and there I'll answer your questions on the new exercise 1, which, by the way, is already out. You can download it from It's Learning. Here is exercise 1. I've already done that, and it is here. So you see, you have some theoretical work to do, and then also some programming work. And you have also 2 optional exercises, deriving the solution for the equation, and also to be a little bit more sophisticated in your MATLAB program. Okay, so, but let me repeat, are there any questions at the moment regarding the lessons? If not, I'll put what we just decided on, and when I have the room, on Wednesdays 12 to 14, I put that then on It's Learning as a note. Okay, and regarding the book, I plan to put on the It's Learning page in the 2nd edition. This is the 3rd edition, and then that is meant for your personal use, just for this course. It's not for spreading it, but just for having a reference. Sometimes it's useful to have it. For those who have the book, it's of course best, then you have the latest version and can look up the details. Okay, we have still left regarding the derivation of the Navier-Stokes equations, the viscous stress tensor. I promised you to give that. And what we usually assume there is that we have a Newtonian fluid. So we have the viscous stress tensor for a Newtonian fluid. that would be then the number 3 in our equations. My notation, the tau with the double underscore is then a tensor. You could also say it's a matrix. That is the viscosity coefficient, mu, times nabla u. I'll say in a minute what that is, plus nabla u transposed, minus 2/3 times the viscosity coefficient times the divergence of u times the identity matrix, or the unit tensor. And the nabla in Cartesian coordinates is the vector ddx, ddy, and ddz. So that is the nabla operator. In Cartesian coordinates. And the nabla u, you can imagine as a vector or a matrix product. If the vector is considered as a matrix, then it is meant the following. So the nabla u is then meant that we have the ddx as a column vector, ddy, ddz, column vector, multiplied with the velocity vector. In Cartesian coordinates, the velocity components are u, v, and w. And then we have the x derivative of u, so the ux that we have here is then the partial derivative of u with respect to x. We have the vx, the wx, we have the uy, the vy, the wy, the uz, the vz, and the wz. So that is then, and so on. That is just abbreviations. The I is the unity matrix. If you are in 3D, it is 1s in the diagonal and 0 otherwise. And the mu, that is usually just a function of temperature, but it could also be of pressure. That is the dynamic or just the viscosity. Coefficient. So, and this is just the divergence of u, the number of the u. Okay, so then we have the momentum equation complete, and then we want to look up the energy equation. So here we have this. Here we are getting to the energy equation. So let's derive that quickly. In the textbook, you'll find also each equation. We'll look at that later on also for each component in Cartesian coordinates. The form that I prefer here, because it's very compact, is the vector notation. So then it can be essentially any coordinate system. So, energy equation. And that is then based on the first law of thermodynamics. Which tells us, again for the system, that the total rate of total energy change in the system, again, again, we know it only for systems, is equal to the rate of work done on the system by external forces. In our case, we have considered 3 external forces: pressure force, viscous force, and external force. So, plus the rate of heat added to the system. So that is what we know. And then we have just to again use the Reynolds transport theorem to get the total rate of total energy change in the system translated to what it means for the control volume. It will be the same thing as before. We will get the rate of change of the total energy inside the control volume plus the total energy flow over the boundary of the control volume. And then we have simply to find the work done by the external forces and then the heat added, the rate of heat added. So that means with the Reynolds transport theorem, and now applied for the total energy, and that is then the integral over rho p dV, and the total energy here is then the internal energy plus the kinetic energy. I'll give a note on that later. So the total energy, then we have the similar thing as we had before. What happens to this? Let's see. Problem at the moment, but then we can do without. So we have the rho b in T, we have the integral over the control volume omega, and that is the rate of total energy change inside the control volume, plus the integral over the boundary of the control volume, and then we have the total energy flow over the boundary of the control volume. That's a surface integral. So that's the total energy flow over d omega, and that is then equal to the rate of work done by the pressure forces first. That is, therefore we have the minus the omega, and we get that by having here the pressure, and then we get the u dot n dA. So that will give us then the rate of work done by the pressure force. For the viscous force, we have also a surface integral. We can do it that we have the tau dot u, and we have that then dot n, also a surface integral. And so that is the rate of work done by the viscous forces on the surface of the control volume. And we have the integral over omega. We have the external acceleration F. As an example, if it's the gravitational acceleration, it's just the vector g. And to get the work done by that, we do the inner product with the velocity and integrate over the volume. That's the volume integral. So that's the rate of work done by the external forces. So when I write here external forces, I want also to have included, as we call the pressure and the viscous forces. And now we have the heat, the rate of heat added. Then we have one way is by heat conduction. We have the heat flux, the vector Q, dot n. So since that is in opposite direction to the normal, we have the minus here, and that is a surface integral. And a term that I have not included in the lecture notes at the moment, that is the rate of heat produced by external heat sources. So that will be omega, and the heat sources will be then a Q point dV. So that will be the rate of heat produced by an external heat source per volume. If we integrate over all the volume, we get the total. So the interesting terms here that are new to us essentially is the rate of heat produced. And if it's negative, then it is absorbed, it will be then a sink. But if it's positive, then it's a source. So rate of heat produced by external heat sources in the control volume omega. And this one here is the rate of heat added by heat conduction over the boundary, over d omega, over the boundary. So then we have to say something about Q. This is the rate of work done by the external forces. This is the rate of work done by the viscous forces, rate of work done by the pressure forces. This is the total energy flow over the boundary, d omega, and this is the rate of total energy produced inside the control volume. So, and all this here is then the energy. And now the information that I promised regarding the capital E. That is the total energy per unit mass. What we have here, the rho E, is the total energy per unit volume. So that is then equation 5. The E is the internal energy. So that is the specific total energy. Specific always means per unit mass. That is the internal, the specific. Often it is just skipped the name, but it is always meant as specific internal energy. Plus 1/2 modulus of u, or absolute value of the velocity vector u squared, and that is the specific kinetic energy. Specific kinetic energy. Okay, so now that is then how the total energy, specific total energy is defined. And we have later on also to say something about how the internal energy is related to the temperature. So the heat flux vector Q is defined, that is due to heat conduction. That is obtained from Fourier's law. And that tells us that the heat flux Q is opposite to the gradient of temperature. The proportionality constant K is the thermal conductivity. So Q is minus thermal conductivity K times the gradient of temperature. So if we have a constant Prandtl number, we can easily relate the thermal conductivity to the viscosity. So let's see, look at up. This is in most, or in many applications, 0, but we will have also examples where this is not 0, where we will have an external heat source. But otherwise, it is made up of these contributions. And you will see in exercise 1, you can simplify that very much to get the heat equation. And to understand the assumptions, you do the derivation, and then you make all the assumptions necessary to arrive at the heat equation. So that will be part of exercise 1. Okay, so the idea of having a constant Prandtl number and that is what you often can assume in applications that is the case. That means that PR is Cp, specific heat at constant pressure, times the viscosity coefficient divided by the thermal conductivity, that is constant. So that is the Prandtl number, named after Ludwig Prandtl, the famous fluid dynamicist in the 20th century. So if that is constant, then let me first say what the Cp is, where the Cp is the specific heat at constant pressure. For example, air at standard conditions is about 0.72. Standard conditions are 1 atmosphere and I think 20 degrees. So in that case, the thermal conductivity K can be obtained from saying this is equal to some This is simply constant. And if we know the number, for example, for air 0.72, and we know the Cp, we know the mu, we can determine the K. So, and that is then the following. Then the thermal conductivity K is equal to the specific heat at constant pressure divided by the Prandtl number times mu. So then we only need to determine the viscosity, and then we have the thermal conductivity. So then we have derived the basic equations that in computational fluid dynamics are called the compressible Navier-Stokes equations. The continuity, the momentum, and the energy equations. In fluid mechanics, it is common to call only the momentum equation Navier-Stokes equation or Navier-Stokes equations. But in computational fluid dynamics, it has become common to call the whole set of equations of conservation laws for mass, momentum, and energy the compressible Navier-Stokes equations. So now we want to know a little bit more. We know about E. We want to have there some information. And we want to know how the pressure is related to the density and the temperature. Because at the moment we have too many unknowns. We have only 3 equations. One is a vector equation in 3D that gives us 3 equations for the momentum, 1 for the continuity, and 1 for the energy. So we have 5 unknowns. But in the time derivatives of rho u, and rho e, but we have here, in addition, we have E, we have T, we have the pressure, so we must relate them to each other, and that is done by equations of state. So that is what we look at now, and we shall do what is most common. We shall look at a perfect gas, because there it is quite simple. If you have more complex relations, then you get more complex equations of state. If you get to extreme conditions, for example, if you want to transport CO2, then you have to take that into account. But in our case, we take the simplest way. We look at perfect gas. So the equations of state for perfect gas. So that would be then the first one that you know. Of course, that is the pressure is equal to the density times the specific gas constant R times the temperature. So the gas equation, and the other one that is accompanying it is the relation between internal energy and temperature. That is related by the specific heat at constant volume. So we have these 2 equations, and in here we have that R is the difference between Cp and Cv. So that is the specific gas constant. So it's related to the universal one. I think it's the universal one divided by the molar mass of the gas that you consider. And Cp we have already seen, the specific heat at constant pressure, and the Cv is the specific heat at constant volume. So for perfect gas, these specific heats are constant. And very important is their ratio. Their ratio is called gamma Cp divided by Cv. That is the ratio of specific heats. And the gamma is 1.4 for air at standard conditions. Again, when you come to extreme conditions, for example, from re-entry flow from a spacecraft into Earth, then that will change. You have also other more complex effects, that you have reactions going on, then you can no longer use that. What I ask you to do as a little homework, to derive from these relations the following. So, show yourself the following, that the pressure is equal to gamma minus 1 times rho E, internal energy. And that we can already know from what we saw before about E. We can simply express that, so gamma minus 1 times, that will be then the total energy per unit volume rho E minus the kinetic energy per unit volume. So that means that we can, and gamma is a constant that we know. So, and U is, so that I ask you to derive yourself. And what we also know is that U can be expressed as the ratio of the momentum density and the density. So that means we can then, from all this, we can express the pressure as a function of rho, rho U, and rho E. And also, we can also say that the temperature is a function of rho, rho U, and rho E. So when we know these variables, then we know everything. So that means we can express all the Navier-Stokes equations. So the Navier-Stokes equations, the compressible Navier-Stokes equations, that are the equations that we derive 1, 2, and 4. The continuity, the momentum, and the energy equations can all be expressed as functions of something that is number 10. Let's see if we get that a little bit better. Of the following, that is, we call that capital U. There are different names for that. Let's see. And that is a vector consisting of rho, rho U, which is also a vector, and rho E. So these are called the conservative variables. Called the conservative variables. So that means then that we can, when we know them, we know everything. Because we can then, knowing them, we can express the pressure, the temperature, velocity, so everything is known to us. So that is then the goal, to determine the conservative variables. Okay, so we stop here and we continue tomorrow, finishing up, and then looking at the incompressible Navier-Stokes.